This lecture is going to be on isotopes, and we're going to look at carbon-12, carbon-13, and carbon-14. Carbon-13 and 14 are isotopes of carbon-12. So not all the same elements are the same. Isotopes are atoms of the same element. Notice these are all carbon. They have different numbers of neutrons within the nucleus. The number of protons of an element is the same. So you'll see that the protons are labeled here in red. And there should be 6 protons for each of these. So carbon always has 6 protons and 6 electrons. But notice the isotopes are going to vary from having 6 neutrons in carbon-12 to having 7 neutrons in carbon-13 and 8 neutrons in carbon-14. That most carbon atoms have 6 protons and 6 neutrons in the nucleus. Some carbon atoms have 7 or 8 neutrons. These still have 6 protons and 6 electrons, so it's still carbon. These varying number of neutrons are the carbon isotopes. We're going to start looking at using terms like stable and unstable. A stable element does not decay. Unstable isotopes decay or break down. Carbon-12 and carbon-13 are very stable. Carbon-14 is very radioactive due to an unstable nucleus. Carbon-14 eventually changes itself or decays into nitrogen-14 through radioactive decay. So here's another example. Here's a different isotope. We can look at oxygen. The oxygen isotope is still oxygen. It just has 2 more neutrons in oxygen in O18. So it will break down or decay at a known rate. This is going to be unstable. This will decay. This is very stable. This will not decay. Oxygen isotopes are used to radiometric date air bubbles trapped in glacial ice in both Greenland and Antarctica to determine paleoclimates or ancient climates of Earth. So it's a very, very real application to how isotopes and isotopic ratios using radiometric dating is used. So very, very high quality. And so the weak nuclear force controls the decay rate. When I say the word weak nuclear force, we're really talking about what is holding the nucleus together. That when the nucleus of an atom is unstable, by having too many neutrons, it decays or breaks down. In this process of radioactive decay, energy is given off in the form of radiation. And sometimes this radiation can be really, really dangerous and harmful to people. So here we can look at radiometric dating. We can start putting numbers to it. That radiometric dating provides a numerical age or date of rocks and minerals that contain these particular isotopes, which spontaneously break down or decay to form stable isotopes. So they go from being unstable, they decay, into being stable. The decay rate is often described in terms of what we call half-life, which is the amount of time required for half of the atoms of any starting mass of radioactive isotope to decay into stable end product, which we will call daughter isotope. So radioactive isotope we will call parent, and we'll call those unstable. And stable daughter products are what we'll call the end product is stable, we'll call that the daughter. So after one half-life, half of the parent atoms change into equal number of daughter atoms. And after the second half-life, half of the remaining radioactive isotope would still exist, right? Half of the parent would still exist. And with each successive half-life, the remaining parent isotope would be reduced to half. So let's look at that in terms of numbers. So at the beginning here, I have some value of parent isotope. And so what I can look at here is as I start a reaction, I have the parent, which is unstable. I have 100% of the radioactive material. I have 0% of daughter. It has not decayed yet. We will call this 0 half-life. This would be like our starting point. So we have a 1-to-0 parent-daughter ratio. So it's 100% parent, it's 0% daughter. But after one half-life, this is where we start applying the concept here. That after one half-life, I have 50% parent, right? Half of it's going to decay. It's going to decay into half or 50% stable daughter. Now notice, it's only the parent that's radioactive. This is the only one that's going to be decaying or radioactively decaying into losing value. It's going to be decreasing half of its value each half-life. So let's look at this. The second half-life. Half of this decays, 50%. So half of the half is going to lead to 25% of the original, or 1/4 of the original. And therefore, the other 25% is going to be stable daughter. So let's look at these in terms of ratios. We'll focus on the first half-life. If I have half parent and half daughter, I would call this a 1-to-1 ratio. It's 1 part parent to 1 part daughter. Whereas after my second half-life, I'm going to have 1 part parent to 3 parts stable daughter. So my ratio is a 1-to-3. And therefore, if I continue going through here, my third half-life, it's going to be half of 25%, so 12.5%, which is 1/8 of my original total. And it's going to be 7/8, or 87.5% of my original parent total. This is a ratio of 1-to-7. And then my fourth half-life is going to be half of 12.5, and etc. And you'll notice that these ratios tell me the amount of parent to daughter. And I can use these to calculate the half-life themselves. So now I can apply this to this graph here, and I want you to see here that if I began with 10 grams of radioactive parent, you would have 10 grams of parent to begin and 0 grams of stable daughter, and that's where this would start up here. 100% parent, 0% daughter. But after 1 half-life, half of the parent has decayed. So after I have 50%, which is 5 grams of radioactive parent still, right? Half of it's left. I'm going to have 50%, or 5 grams, of stable daughter. And this is my 1-to-1 ratio. But after 2 half-lives, notice, here's my 1 half-life, here's my 2. After 2 half-lives, the remaining parent would continue to decay. So I had 50% parent, it's going to decrease by half. So I'm going to have 25% of my original 10 grams that is going to be radioactive parent, right? So if I look at this, the remaining parent would continue to decay. So I would only have half of the 5 grams. So that's 2.5 grams of radioactive parent and 7.5 grams of stable daughter. So where I have the 2.5 grams of my radioactive parent, I'm also going to have 7.5 grams of stable daughter. So notice, as I'm losing radioactive parent, I am proportionally gaining stable daughter. And that's why this graph looks the way it does. So the graph shows the relationship as the radioactive parent decaying, it's losing radioactive parent, as the stable daughter is then increasing or gaining. So let's solve a couple problems and try to make sense of both this and a picture that we should be able to see in our binder. So here we go. If I have a ratio of 1 parent to 3 daughter, how many half-lives has the material gone through? Well, 1 parent to 3 daughter, it tells me, let's see, let me find my ratio, 1 to 3. It tells me that it's gone through 2 half-lives. So I can use the ratio to make sense as to the number of half-lives, or I could use the number of half-lives to then calculate the ratio. So if I have a sample that has a half-life of 100,000 years, this is just a random example, and the parent-to-daughter ratio is 1-to-7, how old is the sample? Well, 1-to-7 ratio tells me, well, let's see, it must have gone through 3 half-lives, and each half-life is 100,000 years. So 3 times 100,000 would tell me that this sample is 300,000 years old. So the sample's age would be about 300,000 years old. So let's put it together in more of a story problem. So I have a sample bone from a woolly mammoth that was from the Pleistocene epoch, right, the Great Ice Age. And it has been radiocarbon dated. Radiocarbon has a very specific timeline. Radiocarbon dating. Carbon-14 decays into nitrogen-14 every 5,730 years. This is the half-life of carbon-14, the decay rate. So if I have a sample that has a 1 to 15, 1 parent to 15 daughter, this is my ratio. How old is the sample? So some quick math here. So let's go back first and apply this. Let's get our number of half-lives. 1 to 15 is my ratio. That's 4 half-lives. So I've got 4 half-lives times the half-life decay rate. So 4 times 5,730 tells me that the age of the woolly mammoth bone is going to be about 23,000 years old. So I could say it's actually 29,000 and change. I could say very, very confidently it's about 23,000-year-old woolly mammoth bone. And that's how we apply radiocarbon dating to this scenario. I hope that helps.